Hi guys, I'm back with my lectures. This is Mr. Joseph, your chemistry teacher. Today's lecture is a continuation of our previous lecture on lattice energy. And what is lattice energy? From our previous lecture, we said lattice energy is the enthalpy change when one mole of an ionic solid is formed from its gaseous ions under what? Under standard conditions. Now in practice, it is not possible to form one mole of an ionic solid from its what? Gaseous what? Ions. That means we cannot measure the lattice energy what? Directly. We need other what? Enthalpy what? Changes. And this can be done using what? The Born-Haber cycle. So in today's lecture, we'll be looking at the Born-Haber cycle, why we need the Born-Haber cycle, generic Born-Haber cycle, how we can represent the lattice energy in the Born-Haber cycle, and also how we can represent other quantities in a Born-Haber cycle. Now looking at the Born-Haber cycle, a Born-Haber cycle is a particular type of enthalpy cycle used to calculate the lattice or the lattice energy. And we'll talk about lattice energy. Lattice energy is the enthalpy change when one mole of an ionic compound or ionic solid is formed from its gaseous ions under what? Under standard conditions. Now looking at the enthalpy cycle before us, we have ions in gaseous state to what? Ionic compound. Now from this point to this point, it has to do with the lattice energy, which is the enthalpy change when one mole of an ionic compound is formed from its what? Gaseous ions under what? Under standard conditions. Now from this point to this point has to do with what? The standard enthalpy change of formation of the ionic compound. Elements in their standard state to ionic compound. What is standard enthalpy change of formation? It is the enthalpy change when one mole of a compound is formed from its what? Elements under what? Standard conditions. So from this point to this point has to do with standard enthalpy change of formation of what? Of the ionic what? Of the ionic compound. Now from this point to this point, which is elements in their standard state to ions in gaseous state, we are dealing with an ionic compound. An ionic compound consists of a metal and what? And a non-metal. In the formation of an ionic compound, it has to do with transfer of electrons from the metal to the what? Non-metal. So from this point to this point, we are looking at the enthalpy change of atomization of the metal and enthalpy change of atomization of the non-metal. We are looking at the enthalpy change of ionization of the metal and the enthalpy change of electron affinity of what? Of the non-metal. So from elements in their standard states to ions in gaseous state has to do with the atomization of the metal and atomization of the non-metal. Ionization of the metal and electron affinity of what? Of the non-metal. The Born-Haber cycle works on the principles of what? The Hess's law. And Hess's law states that what? The total enthalpy change in a chemical reaction is independent of the route that is taken, provided that the initial and the final conditions remains the same. What it's trying to explain is that what? Irrespective of the route that is taken, the total enthalpy change of a chemical reaction remains the same. Now in the formation of an ionic compound, looking at the cycle, we might decide to form the ionic compound by combining what? The elements in their standard state to form what? To form the ionic compound. So from this point to this point, that is elements in their standard state to what? To the ionic compound. This is what? One route we might decide to take, which is the direct route that gives us what? The standard enthalpy change of formation of the ionic what? Compound. We might just decide to combine the elements in their standard state then to form the ionic compound, which is the direct route. Now we might decide to take another route whereby what? We bring the enthalpy change of atomization of each of the elements of the ionic compound, and enthalpy change, that is enthalpy change of atomization of the metal and enthalpy change of atomization of the non-metal, enthalpy change of ionization of the metal and enthalpy change of electron affinity of the non-metal to what? To form the ions in what? In gaseous state. That means from this point to this point, after getting the ions in the gaseous state, we'll combine them to form what? To form the ionic compound. So this is another route we call what? Indirect what? Indirect route. That means from this point to this point, and then from this point what? To this point gives us what? Indirect route. So what Hess law is trying to explain is that irrespective of the route that is taken, the total enthalpy change remains what? Remains the same, provided that the initial and the final conditions remains what? The same. That means direct route is equal to what? Indirect what? Indirect route. Now, if you look at what we have here, the direct route is the what? Enthalpy change of formation. Then the indirect route is what? Enthalpy change of atomization, enthalpy change of electron affinity, and enthalpy change of what? Ionization, plus what? The lattice what? The lattice enthalpy. So from this now, enthalpy change of formation is equal to what? Enthalpy change of atomization plus enthalpy change of ionization plus enthalpy change of electron affinity plus what? Lattice what? Lattice enthalpy. So that is how Hess's law, that is how the Born-Haber cycle works. It works based on the principles of what? Hess's law, which states that the total enthalpy change of a chemical reaction is independent of the route that is taken, provided that the initial and the final conditions remains what? The same. So we've discovered that the Born-Haber cycle works on the principle of what? The Hess's law, which states that the total enthalpy change of a reaction is independent of the route that is what? That is taken. That means the direct route, which is the enthalpy change of formation of the ionic compound, is equal to what? Indirect route. Indirect route, which is what? The sum of what? The enthalpy change of atomization, ionization, electron affinity, plus what? Plus the lattice what? Plus the lattice enthalpy. So from Hess's law, the direct route is equal to what? Indirect what? Indirect route. So rearranging this equation, we can get what? The lattice what? The lattice energy. So the lattice energy will be equal to what? Enthalpy change of formation minus what? The summation of what? Enthalpy change of atomization of the metal and enthalpy change of atomization of the non-metal, enthalpy change of ionization of the metal, and enthalpy change of what? Electron affinity of what? Of the non-metal. So from this, we can calculate what? The lattice what? The lattice energy, which is equal to enthalpy change of formation minus the summation of enthalpy change of atomization, electron affinity, and what? Ionization. So this is a typical Born-Haber cycle of what? Lithium or lithium fluoride. So we're going to analyze each of the steps that is involved and each of the process that is involved in each step. Now from the Born-Haber cycle, this is ions in the gaseous state, which is lithium ion plus fluoride ion. Then to give the lithium fluoride, which is from year to year, which is the lattice what? The lattice enthalpy or the lattice what? Energy. Then we'll come to this point, which this is elements in their standard states, which is lithium solid and what? Fluorine gas. Then from this point to this point is the what? Standard enthalpy change of formation, when 1 mole of what? Lithium fluoride is formed from its what? Its element. So from year to year is the what? Enthalpy change of what? Formation, or the standard enthalpy change of what? Formation. Then from this point to this point is the what? Atomization of what? Lithium, which is step 1. Step 1 is atomization of lithium. Then step 2 is what? First ionization energy of what? Lithium. First ionization energy of lithium, that is step 2. Then step 3 is what? Atomization of what? Fluorine, which is from this point to this point, which is atomization of what? Fluorine. When 1 mole of a gaseous fluorine atom is formed from its what? Element. So enthalpy change of atomization of fluorine. Then step 4, which is what? Enthalpy change of what? Electron affinity of what? Fluorine. Electron affinity of what? Fluorine, which is step 4 from this point to this point. When 1 mole of electron is added to 1 mole of a gaseous atom to form 1 mole of a gaseous what? Minus 1 minus 1 ion. So this is a typical analysis of what? The Born-Haber what? Cycle. The enthalpy cycle of the Born-Haber what? Cycle. From this point to this point is what? Is the summation of what? The enthalpy change of atomization of lithium and atomization of fluorine, ionization of lithium, and electron affinity of what? Fluorine. So the Born-Haber cycle has an energy level diagram. So the Born-Haber cycle can be represented using what? The energy level what? Diagram. Now, if you look at the energy level diagram here, you discover that some of the arrows are moving downward and some of the arrows are moving what? Upwards. And there are different stages. Each of the stages represent what? A process. It represents an enthalpy change, which can be enthalpy change of formation, enthalpy change of atomization, enthalpy change of ionization energy, enthalpy change of electron affinity, or the lattice enthalpy or lattice what? Energy. Now, where the arrow moves down represent an exothermic process. Where it moves up represent what? An endothermic what? An endothermic process. So if we are to analyze the enthalpy cycle for magnesium chloride, the first stage here is enthalpy change of formation of magnesium what? Magnesium chloride. You can see the arrow moving down. When we talk about enthalpy change of formation, is the enthalpy change when 1 mole of a compound, which is magnesium chloride, is formed from its element, magnesium or chlorine, under what? Under standard what? Condition. And it's an exothermic what? Exothermic process. You can see from the reactant, this is the reactant to the product. The atoms and the charges are balanced. Like if you look at here, we'll have 1 atom of magnesium and 2 atoms of what? Chlorine. We'll have what? 1 atom of magnesium and 2 atoms of what? 2 atoms of chlorine. Then the charge is 0 and the charge is 0, the charge is 0, the charge is 0. That means the atoms and the charges are also what? Balanced. Then the second stage is enthalpy change of atomization of what? Magnesium. That is the enthalpy change when 1 mole of what? A gaseous atom is formed from its what? Element under what? Under standard condition. And you can see it's an endothermic process because the arrow is moving what? The arrow is moving up. So this is the reactant and this is what? The product. So we have to check the atoms. If you look at now, on the reactant, magnesium is 1, chlorine is 2. On the product here, magnesium is 1, chlorine is 2. The atoms are what? Balanced. So the charge is 0, the charge is 0, the charge is 0, the charge is 0. So the atoms and the charges are what? Balanced. Then the next step, you can see the arrow is moving upwards. It's an endothermic process. That means the first ionization energy of what? Magnesium. First ionization energy of magnesium, which is an endothermic what? An endothermic process. So this is the reactant and this is the product. So we have to check the atoms and the charges to see if they are balanced. Magnesium is 1 here, chlorine is 2 here. Magnesium is 1 here, chlorine is here. So the atoms are balanced. Now let's look at the charges. The charge is +1 and the charge is what? -1, which is 0, and the charge is 0, the charge is 0, the charge is 0. So the atoms and the charges are also what? Balanced. The second stage is second ionization energy of what? Magnesium. Second ionization energy of magnesium, which is an endothermic process. From, as you can see, the arrow is moving what? Upward. And this is what? The reactant, and this is what? The product. So we have to check if the atoms and charges are what? Balanced. The atom is here, magnesium here is 1, chlorine here is 2. Magnesium here is 1, chlorine here is what? 2. So we have the charges, the atom is what? Balanced. Let's check the charges. The charge is +2, -2, which is 0. Chlorine here is 0. Here is +1, -1, which is 0. Chlorine here is also 0. So the charges and the atoms are also what? Balanced. The next stage is what? It's an endothermic process. You can see the arrow is moving up. Is what? Enthalpy change of atomization of what? Of chlorine. And you can see that the enthalpy change of atomization of chlorine is multiplied by what? 2. Because from the formula we'll have 2 moles of what? Chloride what? Chloride what? Ion. So if you have to carry out the calculation, you have to multiply the enthalpy of atomization by what? By 2. So you can see this is the reactant and this is what? The product. So you can check that this is the magnesium is 1 here, chlorine is 2 here. So the atoms here are balanced. Magnesium is 1 here, chlorine is what? 2 here. So let's check the charges. Here is +2 and here is -2. So +2 -2 is 0. So magnesium is 0 here, chlorine is 0 here. +2 -2 here also 0. Magnesium is 0 here, chlorine is 0. So the atoms and the charges are also what? Are also balanced. Then the next stage, you can see the arrow is going down, which is an exothermic process. Exothermic process, which is what? The enthalpy change of what? Electron what? Electron affinity of what? Electron affinity of chlorine. And you can see that the electron affinity of chlorine is multiplied by what? By 2, because we have 2 moles of what? Chlorine what? Chlorine atom. So you can see that this is what? This is the reactant and this is what? And this is the product. So if you check, magnesium is 1 here, chlorine is 2 here. Magnesium is 1 here, chlorine is 2 here. So the atoms are what? Balanced. Let's check for the charges. Magnesium here is +2 and -2, which is 0. Chlorine here is also what? 0. Magnesium here is +2 and -2, which is what? 0. So the atoms and the charges are also what? Are also balanced. Then the next stage is, which is the last stage, is an exothermic process also, which is the lattice what? The lattice energy. And when we talk about lattice energy, is the enthalpy change when 1 mole of an ionic solid, which is magnesium chloride, is formed from its gaseous ions under what? Under standard what? Under standard condition. So you can see that this is the reactant and this is the product. Magnesium is 1 year, chlorine is 1 year, magnesium is 1 year, chlorine is 1 year. So the atoms balance. The charges here is plus 2 minus. So the atoms and the charges are also what? Are also balanced. So you can see the arrow moving downward. So this is the what? This is the what? Lattice what? Lattice energy. So as you can see, it's as simple as what? As A, B, C. You can analyze what? The Haber cycle for any ionic compound that is what? Given. All you need to do is just to identify each of the stages and each of the enthalpy change that is involved, and also represent what? The equations correctly, and make sure that the atoms and the charges are properly what? Balanced. So the Haber cycle as an energy level diagram. This is a typical example of the Haber cycle for what? Calcium oxide, which is an ionic compound, contain what? One atom of calcium and one atom of what? Oxygen, and it's associated to give you calcium ion or what? Oxide what? Oxide ion. So if you look at the cycle before us, it involves what? Different stages, and each of the stages represent what? A process. It represents an enthalpy what? An enthalpy change, which can be enthalpy change of formation, enthalpy change of atomization, ionization energy, electron affinity, or it can be lattice what? Lattice energy. So the first stage we are going to consider, you can see the arrow is moving downward, which is an indication that what? Is an exothermic process. That is the enthalpy change of formation of what? Calcium oxide, which is the enthalpy change when 1 mole of what? Calcium oxide is formed from its element, calcium and oxygen, under what? Under standard what? Under standard condition. So you can see the arrow is moving what? Downward, and we are to check if the atoms and the charges are what? Are balanced. So you can see this is the reactant and this is the product. Calcium is 1 year, oxygen is 1 year. Calcium on the product, calcium is 1 year, oxygen in 1 year. So the atoms are what? Balanced. Now we'll now check out for the charges. The charge is 0 and the charge is 0. The charge is 0, so the atoms and the charges are what? Balanced. The second stage is an endothermic process. You can see the arrow is moving upward, which is what? The enthalpy of atomization of what? Calcium, which is what? An endothermic what? An endothermic process. As you can see, the atoms and the charges are also balanced. Calcium is 1 year, oxygen is 1 year, calcium is 1 year, oxygen is 1 year. So the atom is balanced. Let's go for the charges. The charge is 0, 0, 0, 0. So the atoms and the charges are also balanced. The next stage is what? Forced ionization energy of what? Calcium. So it's an endothermic process also. And in fact, you can see that the arrow is moving what? Upward. So you can see, let's consider the charges and the atoms. The calcium is 1, oxygen is 1, calcium is also 1, oxygen is 1. So the atoms are both balanced. Let's consider the charges. Here the charge is plus 1 and the charge is what? Minus 1 for calcium. So the charge is 0, plus 1 minus 1 is 0, and here 0. Then when it comes to this place, calcium is 0, oxygen is 0. So the atoms and the charges are also what? Balanced. Then the next stage is second ionization energy of what? Calcium, which is what? An endothermic what? An endothermic process. As you can see, the arrow is what? Moving upward. You can see here from here, calcium is 1 year, oxygen is 1 year. So it is what? Calcium is 1 year, oxygen is 1 year. So the atoms are what? Balanced. Let's check the same thing. Calcium is 1 year, oxygen is 1 year. The atom is what? Balanced. Now let's check for the charge. The charge is what? Plus 2 minus 2. So the charge is 0 for calcium. Here the charge for oxygen is 0. The charge is plus 1 minus 1, which is 0 for calcium, and yes was 0. So the atoms and the charges are also what? Balanced. The next stage is what? Enthalpy change of atomization of what? Oxygen. It's an endothermic process. As you can see, the arrow moves what? Upward. And if you have to check, the charges plus 2 and the charges minus 2. So the charges balance, which is 0. Here the charge is 0. Here the charges plus 2 and the charges minus 2, plus 2 minus 2, which is 0 for calcium. Oxygen here is 0. So the charges are what? Balanced. Now we check for the atom. The atom is here. Calcium is 1 year. Oxygen is 1 year. Atom is balanced here. Calcium is 1 year. Oxygen is 1 year. The atom is also what? Balanced, which is what? An endothermic process from the direction of what? The arrow. The next stage is what? The enthalpy change for the electron affinity. Electron affinity of what? Oxygen. Electron affinity of oxygen, which is the first electron what? Electron affinity is an exothermic what? An exothermic process. You can see calcium is 1 year, oxygen is 1 year, calcium is 1 here, oxygen is 1 here. The atoms are all balanced. Let's go for the charges. Here, calcium is +2. The charge is +2 minus 2, which is 0. Oxygen here is also 0. The charge is +2 and the +2 and -2, +2 here, which is -1 minus 1, which is -2. So +2 minus 2 is equal to what? 0. So the atoms and the charges are also what? Balanced. Then the next one is the second electron affinity of what? Second electron affinity of oxygen. As you can see, the arrow is moving what? Upward, which is an indication that it's what? An endothermic what? An endothermic process. Second ionization energy is usually what? Endothermic. The reason is because you are adding what? An electron to a negatively charged ion. So what happens is that energy is needed to overcome what? The repulsive forces between the negatively charged ion and the electron, because you are combining an electron to a negatively what? Charged ion, which is what? An ion. So energy is needed to overcome the repulsive forces of attraction. So that is why it's an endothermic process. You can see the arrow is moving what? Upward, which is the second electron affinity of what? Oxygen. As you can see, calcium is what? 1 here, oxygen is 1 here, calcium is 1 here, oxygen is 1 here. It's the same thing, the charge is calcium is +2 minus 2, the charge is 0, and here is +2 minus 2, the charge is 0. So the atoms and the charges are also what? Balanced. Then the last stage, which is what? The lattice what? The lattice what? Energy is an exothermic process. As you can see, the arrow is moving what? Downward. As you can see, the arrow is moving what? Downward, and it's an exothermic what? Exothermic process. So lattice energy is the enthalpy change when 1 mole of what? An ionic compound, which is calcium oxide, is formed from its gaseous ions under what? Under standard condition. You can say calcium is 1 here, oxygen is 1 here, calcium is 1 here, oxygen is 1 here. So the atoms are also balanced. Then if you look at the charges, also the charges +2 minus 2, 0, and here is 0. So the atoms and the charges are also what? Balanced. So as you can see, it's as simple as what? A, B, C. You have to follow each step and what? Be able to represent what? The equation, and also what? Be able to represent what? Each of the stages that is what? That is involved. So this is the Haber cycle for lithium what? For lithium fluoride, which is an example of what? An ionic compound, lithium fluoride. It contains 1 atom of lithium and 1 atom of what? Fluorine. So it dissociates to give you lithium ion and what? And fluoride what? Ion. So looking at the Haber cycle as usual, it contain what? Different stages. The first stage is what? Enthalpy change of formation of lithium. When 1 mole of lithium is formed from its what? Element under what? Under standard condition. As you can see, it's an exothermic process because the arrow is moving what? Is moving downward. So as you can see, this is the reactant and this is what? This is the product. So you can see that the atoms and the charges are what? Balanced. Lithium is 1 here, fluorine is 1 here, lithium is 1 here, fluorine is 1 here. So the atoms balance. Let's look at the charges. The charge is what? 0, and the charge is 0. Charge is 0, 0. So the atoms and the charges are also what? Balanced. The next stage is what? Enthalpy change of atomization of what? Atomization of lithium. You can see the arrow is moving what? Upward, which is what? An endothermic what? An endothermic process. You can see this is the reactant and this is the product. Lithium is 1 here, fluorine is 1 here. Lithium is 1 here, fluorine is 1 here. So the atom balance. Then let's look at the charges. The charge is 0 for lithium, 0 for fluorine. Here the charge is 0, the charge is 0. So the atoms and the charges are also what? Balanced. The next stage is what? First ionization energy of what? Lithium, which is what? An endothermic what? Process also. And you can see that the atoms and the charges are also what? Balanced. From the movement of the arrow, it tells you that what is what? An endothermic what? An endothermic process. You can see that this is the reactant and this is what? The product. So what happened? Lithium is 1 here, atom is balanced, lithium is 1 here, lithium is 1 here, lithium is 1 here. So the atoms balance. Then let's look at the charge. The charge is +1 minus 1, which is what? 0, and the charge is also what? 0. Here the charge is 0 and the charge is what? 0. So the atoms and the charges are also what? Balanced. Then the third stage is was an endothermic process also, which is the enthalpy of atomization of what? Fluorine, which is what? An endothermic what? An endothermic process. So this is the reactant and what? And this is what? And this is the product. So the charge is +1 and the charge is -1. +1 minus 1 is 0. So the charge is balanced. Fluorine is also 0. Here the charge is +1 minus 1. The charge is balanced. atom. Lithium is 1 here, fluorine is 1 here, lithium is 1 here, fluorine is 1 here. So the atoms and the charges are also what? Balanced. Then you talk about step 4. Step 4, you can see, is an exothermic process, which is the enthalpy of what? Electron affinity. That is the first electron affinity of what? First electron affinity of fluorine, which is an exothermic process. From the direction of the arrow, you can see there is an exothermic what? Exothermic process. So this is the reactant, and this is what? The product. Lithium is 1 here, fluorine is 1 here, lithium is 1 here, fluorine is 1 here. The atoms are what? Balanced. The charge here, +1, -1, 0, and fluorine here, the charge is 0. Here the charge is +1, -1, which is what? 0. So the atoms and the charges are also what? Balanced. Then the last stage, which is what? The step 5, which is an exothermic process. That is the lattice what? The lattice energy, the lattice enthalpy, which is the enthalpy change when one mole of an ionic solid or ionic compound, which is lithium fluoride, is formed from its what? From its gaseous ions under what? Under standard condition, and is what? An exothermic what? An exothermic process. So it's as simple as ABC. You can represent, other ionic compounds using what? The Haber cycle as an energy what? As an energy level what? Diagram. So before us is a typical examination question for us to analyze. So the Haber cycle for magnesium chloride is shown. So you can see the Haber cycle for magnesium chloride. Then the first question is explain why enthalpy change 4 is greater than enthalpy change 3. What that question is trying to tell us is that what? This is enthalpy change 3 and this is enthalpy change 4. What the question is trying to explain is that what? Explain why the second ionization energy of magnesium is greater than what? The first ionization energy of what? Magnesium, because enthalpy change 4 is the second ionization energy of magnesium, while enthalpy change 3 is what? The first ionization energy of what? Magnesium. The answer is the second electron is removed from a more positively what? Charged ion. So more energy is needed to remove what? The second electron. Then the next question is, what names are given to the enthalpy change? Enthalpy change 6 and enthalpy change 7. So enthalpy change 6, as you can see from the Haber cycle, is what? Is lattice energy. Enthalpy change 6 is lattice energies and is an exothermic process. So you can see the arrow moving down. While enthalpy change 7 is also an exothermic process, is enthalpy change of what? Formation. Enthalpy 7 is enthalpy change of what? Formation. So you can see it's as simple as what? A, B, C. So I advise you to solve as many questions as possible. I'll be leaving a task with you, and please, I want you to handle this task, and if you encounter any difficulty, feel free to reach out to me. I'm always there for you. Please solve as many questions as possible. As you can see, it's very, very simple. So once more, I'm Mr. Joseph, your chemistry teacher. So I'll be leaving a task with you. So this is the task I'll be leaving with you. So please, I want you to attempt these questions. They are very, very simple, and I believe you can do it. And if you encounter any difficulty, feel free to reach out to me. So these are the questions. The next one is identify the enthalpy change level by the numbers 1 to 4 in the cycle. So they are simple as ABC. So please attempt these questions and we'll meet in our next class. Thank you for listening. I'm Mr. Joseph, your chemistry teacher once more. Feel free to reach out to me. I'm always there for you. Please subscribe to my YouTube channel. Go to the comment section and give your feedback. Thank you very much. So Mr. Joe, your chemistry teacher. Thank you very much.